So in this video, we're going to look at graphs and analyze their key features as well as graphing functions given some of those features. So here we have a function. I could say it's a piecewise function, and we're going to analyze every single detail about this function from left to right. So let's have a look at f prime. So over here on the bottom, I'm going to create a table of values, like a first derivative chart, and then the next column, next row will be second derivative. So over here, I'm going to just put down f prime. And each of these dots here refers to a specific point from A to M. So let's have a look at the critical points. Let's actually classify each as a critical point or not a critical point. So recall that critical points over here in the right hand corner, critical points are points where the slope is 0 or the slope is undefined. Meaning, let's talk about undefined. An undefined slope means a slope that you cannot have a value, so ideally a vertical tangent, or another way to look at undefined or not defined slope is where you cannot find the slope at that point. So let's have a look at A. So A, I'm going to classify this as an endpoint. So put here EP for endpoint. Also here, this point here is also a EP endpoint. They're the ends of the graph. So let's actually look at whether this is a critical point. So critical point is, the question is this point here, I'll use red, a critical point? And in this case, it is a critical point. And you're wondering, well, why is that the case? It's not a vertical tangent and the slope is not 0. So why is it considered a critical point? Well, keep in mind, you have to understand that the derivative is the slope of the tangent. So remember what slope of the tangent means by definition? You should be able to draw a slope to the right and a slope to the left. But however, there is no slope to the left, so we cannot draw physically a tangent line there. And because we cannot draw a tangent line, we cannot find the slope, and therefore the slope does not exist. So the slope is not defined there. So the endpoints are, so these 2 points here are considered CP, CP. Let's look at B. B, well, it's a CP because the slope is 0. Over here, the slope is also undefined. It seems like it is a corner-ish type of behavior. So put here CP. Over here, this is also a CP. It looks like a cusp. Okay, so let me just sort of describe the difference between a corner and a cusp. I think we talked about this in previous lessons, but definition of a cusp is the slope is approaching a vertical tangent. So I can draw a vertical tangent here. And also a second part of the definition of a cusp is the concavity is the same on both sides. So meaning at this point here, this is curving down and curving down. Now this one here, we cannot call it a cusp because notice here that from the left, it's curving up, whereas this is curving down. So they're opposite. They're opposite. So keep in mind, cusp, the concavity is the same. They both curve down or curve up to the left, to the right. So this, by definition, the new part of the definition of cusp, it is not a cusp. This one here is a cusp. All right, let's move on. This here is a CP because it's a critical point. The slope is 0. Over here, well, there is no point at F, so this is not a critical point, but we can call F a critical number because it's an X value even though there's no Y value. Now G here, is the slope 0? No. Is the slope vertical? No, it's not. Is the slope, can you draw a tangent there? Yes, you can draw a tangent there, but the slope is negative. So this here is not a critical point. Over here, I'll put here CP. So this is sort of like a cusp. Notice here it curves down and curves down. So it could be a cusp, or depending on what you see, you can consider it a corner. It's up to you. It's it's a bit subjective when it comes to graph. Here is CP. This here is not a CP because the slope is negative. If I were to draw a tangent line there, it'd be a negative slope. Here is CP. This is not a CP. This is a CN, and this is a CP. So all of these CP, CP, CPs are where the slopes are undefined or 0. So the next thing we're going to look at is turning points. So some of them can be classified as more than one. So over here, this is not a turning point. I'll use a blue. So this is not a turning point. This here is a turning point. I'm going to call this a local minimum. So we're going to classify all turning points. This here is not a turning point because a turning point by definition is when the slope is 0. Yes, it does go up and down, but the slope here is not equal to 0. Not a turning point because the slope is undefined. Here is a turning point, but TP. In this case, this is a local max. Not a TP. Nope. This is not a TP. Turning point, a local max. This is a local min. And this is nothing. So the endpoints that you might think it's a local minimum, but you don't know what's going to happen to the right. So this piece is missing the right-hand side, and you cannot make a prediction. Okay. So now we're going to actually look at the increasing, decreasing between the intervals. So let's have a look at A. So A is over here. What's to the left of A? There's nothing, so I'm just going to put a slash here. What happens between A to B? So between here to here in blue, the slope is negative, and over here between B and C, the slope is positive. So all you're looking at for the first derivative row is whether the slope is positive or negative. So here it's negative, over here it's positive, then it's negative. I'll put here 0 for E. D, I'll put undefined. B, I'll put 0. And A is undefined. So I'm actually addressing all those critical points. Over here, between here to here in blue, the slope is negative. These are all negatives. What's happening at G? Well, the slope is still negative. H is undefined. I'll put U for undefined. This is a tight spot here in blue. It's positive. Here it's negative, negative, negative. So it's all negative, negative, negative. And at I here, it's also 0. K, the slope is 0 over here. This is K. Here, the slope is, from here to here, the slope is positive, and then negative. And then we can't have anything to the right because of M, because it's restricted. So the next thing we're going to look at is at the second derivative. So second derivative speaks about refers to concavity and inflection points. So let's look at all the concavity intervals from left to right. So we know from A here, I'll put here A, there's nothing to the left, so there's no curvature to the left in this area here, so I'm going to put an X there. But let's look from left to right. What happens from A all the way to C? It's curving up. So this is all second derivative is positive. So from A to C here is positive. So I'm going to put positive, positive, positive. Then what happens afterwards? This is curving down. So between C to D is going to be negative, 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 negative. And what happens from D all the way to F? It's always curving down. So put here positive, 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 positive. F, there's a vertical asymptote. So I'll put a little vertical asymptote notation there. Now what's happening here? So over here, it seems like this is curving up, and then after that it curves down. So if this curves up, that means from F to G, it's going to be concave up. But then after G, which is this one here, it curves down. So down, down. All right, let's move on from G to H. It's a bit close, so this is always curving down. So this area here that I'm drawing here from H to J, it's curving down. So in this case, if I'm going to put here negative, negative, negative. And then after this point here, after J, it seems like it's curving up. So from J to L, it is positive, positive, positive. Then we have a vertical asymptote. And at the end, this seems like it's curving up. So that means the second derivative is positive. So now we've figured all the intervals of concavity. Now let's look at the points between the transition, whether we have an inflection point. So let's have a look at the inflection point. So inflection point occurs where it becomes positive to a negative. So let's look from here to here. So if you notice here, right over here. So we have positive, 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 and then we have a negative. That means something is happening between here. Let's have a look at C. What's looking at C? C, oh, it's actually a point, a defined point. And by definition of an inflection point must have a defined point, and it must be continuous. There's no gaps or no jumps here. And look at the signs of the concavity, they switch. So we can conclude that this point here is an inflection point. Now this inflection point is not your conventional one, like the ones that you usually see, for example, over here, like the cubic-like feature, but this by definition is an inflection point. So over here, I'm just gonna use in black, this is an inflection point. All right, let's keep on going with this table. So as I move the table from left to right again, what's happening here? So over here, oh, we have a negative to a positive. So what's happening at D? D, wait a second. This is curving I made a mistake here. So as you can see here, between here to here, it's curving down, curving down. So when I actually made a mistake here, might as well just correct it right now. This whole thing should be all negative, 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 negative. So I'm sure that whoever saw the mistake, you must have mentioned, wait a second, this is incorrect. So it's all negatives here because it's curving down, curving down. Okay, so let's move on to the right-hand side. Let's look for more transitions. So look at here. Oh, we have a positive concavity and then a negative concavity. So let's look at point G. G, yes, this is definitely a inflection point. So G is an inflection point. Let's keep on going. Let's look, move on, move on, move on. Oh, then we have a negative to a positive. So negative concavity to positive concavity. Let's look at the J right over here. Yes, curving down, curving up. So G and J are inflection points. And these are all positive, positive, positive. So we have no more inflection points. So in this particular function, we have 3 inflection points over here, and over here. And let's put a value at those specific points. So let's have a look at C, because this is C. So if I put C here in the interval chart, what goes right over here? Well, to be honest, when it comes to finding the second derivative at this point here, I'm going to say right now, let's call this undefined. There's a reason why. There's actually a connection between the slopes, the first derivative and the second derivative, and over here I know that the slope is not 0, so therefore I can make the assumption that the second derivative will not be 0. I'm going to call it undefined. Let's look at the nether transition. What's happening here? For those that are interested at what happens at D, so at D, the first derivative is undefined, and by default the second derivative at D will also be undefined. F is also undefined, but it's a critical number. It's a vertical asymptote. Now over here, what's happening with G? G, all right, in this case, it's going to be, the second derivative will be 0. Because the reason why I know this is because the slope here, there's a real number for slope. So the second derivative will be 0. Over here at J, over here J, the slope, the second derivative will also be 0 right there. H, for those that are interested, it's undefined because the first derivative is undefined. Over here, I think that is it. So here we have a rational function, and I think now's a good time to pause this video and fill in the blanks for each of the rows, and then we'll look at the limits later on. So for the first one, this is just asking you about the y values, where they are below or above. So at negative 100, which is all the way down here, I know that the value will be negative. At negative 2, which is somewhere around here-ish, it's also negative. At negative 1, it's negative. If you want to be specific, you can actually put a number here. At 0, undefined, because there's a vertical asymptote right there. At negative 0.5, which is over here, I believe, 1, 2, 3, 4, 5. Nope, it's right over here. That means it's somewhere right over here in the negatives. At 1, it's going to be 0, right over here where this black dot is. 100 is going to be positive. So you're just figuring out the y values, or the signs of the y values. The next one is f prime. Now f prime refers to the slope. What's the slope over here? All the way here. Well, read a graph from left to right. The slope is positive, positive. And over here, right at negative 1, is a turning point. The slope is 0. Vertical asymptote, the slope is undefined. At negative 0.5, which is somewhere over here, the slope is positive. At 1, right over here, the slope is also positive. Seems like this whole entire right-hand side is always positive. Now the last one, let's look at the concavity. So the concavity is, as I can see here, it's curving down. This is also curving down. So in that case, everywhere is going to be negative second derivative, aside from here. So now, because of vertical asymptote, we're going to call it undefined. Okay, so let's have a look at the end behaviors. I think we talked about it in the previous video, but let's just look at this. So infinity means as x gets bigger, what happens to the y? Well, the y's are also getting bigger. So put here infinity. As you go to the left, as you move to the left, the y values are also approaching negative infinity. Now over here, what does this mean? So this means what is happening to the slope as the graph keeps on going to the right. So as you can see here, the slope seems to be of the end behaviors of the purple graph seems to be wanting to get closer to this vertical asymptote, or sorry, this linear oblique asymptote. And what is the slope of the linear oblique asymptote? If you were to calculate the slope, it'd be, in this case, it'd be 1. So in this case, the slope of this LOA, or slant asymptote, is going to be 1. In other words, it's going to approach 1. Same thing for the left. It's also going to approach 1. The slope is from left to right, so it seems like it's going to be linear at the end behaviors. All right, this one here talks about the concavity. So what happens to the concavity as you move from the middle of the graph to the, so you can see the curvature here, but over here it seems like the graph here, the function is becoming very linear. And when you become linear, what happens to the curvature? You don't have that much curvature. And in other words, the curvature is pretty much getting closer to 0 for both cases. To finish this question off, critical numbers are where the slope is, critical numbers are the x values where the slope is 0 or undefined. So I can tell here, right over here in the red, the slope is going to be 0. So that's an x value, the critical number. But also there's a critical number, even though it doesn't have a y value, at the vertical asymptote. Critical points, well, there's only one critical point because a critical point has x and a y. So it's going to be over here at x is equal to -1. So now we're going to actually do the reverse, where you are given all the information about the y values, the slopes, and the concavity, and your goal is to graph it as best as you can based on the information. So right now, I actually drew all the x and y points. So these are the x's and these are the y's. So the first row tells you the specific point. So that's why you see all these blue dots here. These are specific points. And now we're going to have to somehow connect these dots if possible. Now let's have a look at the first part. What's happening at -9? So here's -9. So it seems like here the slope is 0 or flat, meaning there could be a turning point. Well, what makes it a turning point is the following. This one here, the curvature tells you it's curving down. So that means in blue, I'm going to be, or I'll use red, it has to curve down. So notice here, I just did a little curving down here. And what happens afterwards? This is where I have to go down. So meaning this here, I'm going to have to go down. I'm going to join up with this dot here. So right here, I have to curve down as best as I can. Okay. And what happens at -7? So it seems like, so the slope is negative, but notice here, the second derivative is 0. And look to the left and to the right. The concavity is opposite from each other. So that means this tells me that this is a inflection point. You know what? Let's actually look for all the inflection points here. So over here, the slope is, the second derivative is 0, but notice the concavity is opposite. So this is here is also an inflection point. I'll put I and F because there's a y value. I actually know the y value. Over here, this is also another inflection point because the signs of the concavity are concave down and then concave up. And there's a dot there, so it's a y value. What else is there? Oh, okay, so now we have another inflection point because the inflections are positive, concave up, and then concave down with a y value. So we have a lot of inflection points here. Okay, so let's actually continue on. So if this here is an inflection point, this curves down, and then I have to curve back up. But let's see what's happening at -5. So -5, I have to curve up, and it seems like the slope is 0, so it's a turning point. And this actually tells me the turning point. I need to go down to the left and go up to the right. So I'm going to curve back down and then curve back up. Now what happens at -3, which is over here? There is another inflection point. So I need to curve up, which I am doing right now, and I need to curve back down. Curve down. All right, so what happens here now? So let's look at this section here because we're at 0,4 right now. It is an inflection point, but hold on. The slope is 0. What that means is I need to take my graph and accentuate the flatness at this point. Now, notice over here, it's not flat. Well, why? Because at -7, right over here, which is over here, the slope better be going down. Whereas here, I have to flatten off because the first derivative says to flatten off, okay? So after that, it's all good. It's positive, positive. I need to curve up. So I have to curve up as best as I can. So here is a curving up. So now we're at 5 right now. What's happening at 5? I got the dot. I have a inflection point, and I better be having this positive slope. So I cannot flatten off. So I'm going to have to curve up with a positive slope, and then I need to curve back down. And over here, I'm right here right now. Okay. So it's curving down, curving down. And what happens here at the end behaviors? Notice how 100 and 200 are way off my scale. This actually tells you something about the end behaviors. And if you notice, as I get bigger, as the x gets bigger, it seems like it's approaching a horizontal asymptote at where? At 10. So over here, I'm just going to draw a dash, 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 indicating a horizontal asymptote. And all I'm going to do, and what's the behavior here? I have to be always going up, and I'm going to have to curving down. So I'm just going to keep on going, curving down, curving down, curving down, curving down. Now, curving down doesn't mean I go down. All right, curving down is just the curvature is just facing down. It doesn't have to be a full like parabola curvature. In other words, I don't need this part here, and I can't go back down. And the reason why I can't go back down is because notice the positive slope. I always have to have a positive slope. In other words, I have a horizontal asymptotic behavior, and this is our graph. Over here to the left, you can just put an arrow there, extend it if you want, because it is curving down. So you're forced to curve down to the, well, we don't really know what's happening to the left of -1, but we'll assume that it's curving down.